So I'm going to start off with our 21.3 A and B notes. The A notes, we're just going to focus on the left-hand column here. We'll get to the B notes another day. I want to start off with a little example on the computer. So what I have here is let me reset it for you. I have an example here that will show me if I want to say that I have all of these candies in this candy machine, and I know that the probability of choosing an orange is 40%. That's my probability. And I want to draw a sample, and I want to see if within that sample, do I get 40% orange? So here's what I'm going to do. I'm going to type in one sample, and it's going to randomly choose 25 candies. And it looks like my probability, or my percentage of orange, I should say, is exactly 40%. Now, is that always going to happen? Well, if you notice down here, there's a point plotted down on my graph. Can you see my mouse? I don't know if you can see my mouse. But down on the graph, there is a, let's see if I can. Nope, not going to work. Here we go. All right, so down here, hang on, getting all technological here on you. So down here, I have a point plotted on the graph that represents the proportion that was orange from this most recent draw. So now I'm going to draw another sample. So my first sample gave me 40% orange. My next sample, does it give me 40% orange? It gives me 0.440 or 44% orange. So down here again, there's another dot for 0.44. So even though the probability of orange should be a 40% or 0.4, this one is close to 40%, but not quite exactly. Now if I draw another one, do I get 40%? Should be around there. Another 4.40. Another one. And let's just see if we were to do another 0.44. What if I did 10 samples? Now I'm going to turn off the animation so we don't have to watch all 10 samples being drawn. But if I did 10 samples, you notice all of these dots appeared on my graph down there. And it looks like there's definitely something that is more popular than the others. What if I did 100 samples? Notice my total on my graph is 14 samples right now. Now let's see what if I drew 100 samples. Interesting. What if I drew 1,000 samples, looking at my graph on the bottom? What if I drew 10,000 samples? So this is 11,114 samples that have been drawn. Each time drawing 25 candies. The proportion of orange, that should look like a familiar type of a shape right there. Now I'm going to draw in, or I'm going to shade in a shape that we should be familiar with. And it looks like the more samples that I take, the closer this becomes much more normal. It follows our normal procedure, or our normal distribution. So when we draw samples, the more samples that we use, the more random samples that we use, the closer we get to a normal approximation. Now, does that always happen? And the answer is no, that doesn't always happen. So, starting off with our notes here, let's see, getting back to here, when we have a couple new terms that we got to learn here. Get myself back up here. Okay, so when we have, the first thing we have to see is actually step 3. Now step 3 is all the way back down here, but we have to see, are these two things true? If those two things are true, and I'll talk about how to find those in just a minute, if those two things are true, then yes, the more samples you choose are going to follow that normal pattern. So we need to see if that's true first, and if we know that that's true, then we can use everything that we know about the normal curve. So, let's see. So starting up here, we have some new words that we need to know. first off, we know mu, we know sigma, we know n. Mu is the mean of the population, sigma is the standard deviation of the population, and n is the number of items in a sample. So that example that I just showed you with the candy, n would be 25 because each time we took a sample, we took 25 candies. X bar is the mean of the sample. P is the proportion of successes in the population. And this we would say P hat, has this funny little hat on top. That's the proportion of successes in the sample. So some things that we need to know. When we're looking for, or when we're talking about the mean of the sampling distribution of the sample proportion, mu sub P hat is equal to P. So the mean of the proportion of the successes of the population is equal to the proportion of the successes in the population. There's this other formula here that tells us how do we find the standard deviation if we know some of that information. And we're going to use that in just a minute. So I'm going to come down here to part A. Okay, we have a problem here. It says, suppose that boxes of cereal have a mean mass of 323 grams with a standard deviation of 20 grams, and that 40% of those cereal boxes have a prize inside. We're going to focus on that 40% today. The mean and the standard deviation, we're going to use most of that tomorrow. But my question is, what is the probability that when you pick a random sample of 25 boxes, that the sample proportion has at most 37% with prizes? So, first thing I need to see, I need to figure out, sorry, moving some things around here. First thing I know is that mu sub P hat is equal to the P value, which is equal to 40%, and we're going to call that 0.4 for our calculations. So the mean of the proportion of the population, we've got 40% as successes there, or as ones that would have prizes. Our n value is how many are going to be in a sample. We have 25 boxes in a sample. So we have n is 25, we have p is 0.4. That's enough to start using my process here. So n p has to be greater than or equal to 10. Well, if n is 25 and p is 0.4, let's see what that gives us. 25 times 0.4 is 10. Not sure why I've got all these decimals there. Hang on, let me try and fix my calculator here. Okay, I think I've got it cleared there. 25 times 0.4 gives me 10. Is that greater than or equal to 10? Just barely, but yes, because it is indeed that equals part. So now let's try the other part. Does n times 1 minus p also give us a value that's greater than or equal to 10? So does 25 times 1 minus 0.4 also give us something that's greater than or equal to 10? Well, 25 times 1 minus 0.4 is 15. Is 15 greater than or equal to 10? Yes. So because we meet the requirements, we can treat this just like the normal curve stuff that we learned the other day. So what I want to know is at most 37%. So I could draw a bell curve and I could put percentages on the bottom. It gets a little confusing when we're trying to do that. So I'm going to go ahead and use a z-score. I'm going to see what a z-score of 37% is. So I need to do, for a z-score, that would be the mean of the population, also known as P, which is 0.4, minus, 0.4 is what I'm subtracting there. The mean of the whole thing that I'm looking for, the mean of interest, is what comes first. That's 0.37. So 0.37 minus 0.4 all over the standard deviation, but I don't know what the standard deviation is. I know what the standard deviation of the whole thing is, but not the standard deviation of the proportion. So I need to come up here and do some work. So the standard deviation of the proportion, that would be equal to the square root of p, which is 0.4, times 1 minus 0.4, all divided by n, and in our case, n is 25. So that's how I'm going to find the standard deviation. So let's see. 0.4 times 1 minus 0.4 is 0.24 divided by 25, ugly decimal. I need to square root that answer, and I get 0.097, we'll call it 0.98, we'll round that off there. Sorry, the sun's kind of coming in and out here. It's okay if it blinds that part because we're doing the other side. So that's what goes on the bottom, 0.098. Again, I have the mean or the percentage that I'm looking for minus the percentage of the whole population divided by the standard deviation. So once more, the percentage I'm looking for, the percentage of interest, sometimes they'll say, what are you interested in finding out, minus the percentage from the whole thing divided by the standard deviation. So if I solve that right there, I get, let's see, 0.37 minus 0.4 divided by 0.098, and I get negative 0.31. Now I want 2 digits there because I'm going to need to go use my z-score table, and I need 2 digits for that. So if I go to my z-score and I look up negative 0.31, negative side, 0.3, the first one would be 0.30, the second one would be 0.31. So I have 0.3783. Now remember, our z-score table tells us the percent below that value. So we are looking at the percent below 37%. Does at most 37% mean below 37, or does it mean above 37? Well, at most means that 37 is the highest it could be, and it wants to know everything below there. So this is the percentage we're looking at. 37.83% would be our answer. And if they wanted to know what was above 37%, I would have to do 100% minus this in order to get that result. Okay? So I know that's a little bit confusing. You'll see several of those today. Let's see if I can move this at all to change this. Okay, I think that's a little bit better. So our next part, for random samples of 80 boxes, so our sample size has changed. Since our sample size has changed, anything that has an n in it has to be recalculated. Therefore, my standard deviation is going to have to be recalculated, and I have to recheck because both of those involve an n value. So let me recheck this. NP, my new n value, is 80. And my p-value is still the same. That has not changed because we're still talking about the initial population having 40% as our prize values. So if n equals 80, let's try this NP. So 80 times, can't see where I'm pointing, 80 times 0.4. I need to see if that's greater than or equal to 10, and I also need to do 80 times 1 minus 0.4 to see if that's greater than or equal to 10. So on my calculator, 80 times 0.4 is 32. That's greater than 10, so that's good. And 80 times 1 minus 0.4 is 48. And yes, that's greater than 10. So I've checked it out. It's all working out, so I can say that it is approximately normal. It does fit the same pattern as anything else using the normal curve. Now, they're asking about 68%. Now, I could go through the whole process that I did for the last one, find the z-score, yada, yada, but 68% sounds familiar to me. And if I think back to here, we remember that 68% is simply 1 standard deviation below and 1 standard deviation above. So if I'm looking for an interval that captures 68%, I just need to find out what these two values would be on the normal curve, and then that defines my interval. So I need to take the mean and subtract 1 standard deviation to get this value, and I need to take the mean and I need to add 1 standard deviation to get that value. So what is my mean? Well, my mean is the same thing as the p-value. So that is 0.4. And now I'm going to add 1 standard deviation, and I'm going to subtract 1 standard deviation. So let's find the standard deviation, because I said we'd need to calculate that again because we have different values now. So instead of 0.4 times 1.4 divided by 25, now I need to divide it by 80. So, let's see, where can I put that? I'm going to do, running out of room here, square root of 0.4 times 1 minus 0.4, all divided by 80 instead of 25. So 0.4 times 1 minus 0.4, enter, divided by 80, and then square rooting that answer gives me 0.55, we'll call it, and 0.55. So the subtracting 1 standard deviation gives me this marker, and adding the 1 standard deviation gives me this marker. That will give me my interval. Now, you really don't need a 1 on the outside of parentheses. However, what if it said 95% instead of 68%? Well, 95% is another one of our good numbers. I would be taking away 2 standard deviations and adding 2 standard deviations. So the only difference would be changing these 2 numbers to 2's. So I do put the 1 there just to remind myself that if it wasn't 1 standard deviation out, I would have to change that. So let's see. 0.4 plus 1 times 0.55 gives me 0.95. I think I typed that wrong wrong. Hang on. 0.4 times 1 minus 0.4 divided by 80, square root of the answer. It's 0.055. Aha, 0.055. So I should not have a decimal there. I should have a decimal before the 0, not after the 0. I was wondering why that wasn't coming out quite right. Okay, so there's my 0.055. There we go. So let's try that again. 0.4 plus 1 times 0.055 is equal to, not 0.095, it's 0.455. And then the other one would be the same thing, but it would be a minus, and that gives me 0.345. So this is 45. Okay, sorry about that. I had to pause that for a phone call. So I'm back at 45.5%. And this would be 34.5%. And again, they're looking for an interval, so you would say anywhere from 34.5% to 45.5%. That is the interval that captures 68% of the sample proportions. Okay, now, quick little comment about your homework. Hang on just a minute, let me get that for you. So what I wanted to mention about your homework is that in your homework they do an interval problem like this, but they don't say something about the captures. They give you 2 values. So you're going to have to find the bigger one and then subtract the smaller one like we've done before. But they don't give you percentages. They say 12 to 24. So you're going to have to turn those into percentages. They are sampling 60 students. So 12, you would take that to 12 out of 60 and turn that into a percentage. And 24, you would say 24 out of 60 and turn that into percentage. And again, the way you would turn it into a percentage is you would turn it into a decimal. That's 20%. And then 24 should be 40%. 24 divided by 60 is 40%. So what they're really asking is 24 to 40%. So you're going to want to find the two different values, probably like the first example, and then subtract the bigger one minus the smaller one. Okay? All right. Happy studying.